Alrighty, so we were working on our labs and we had gone over the digits first, just as a reminder. And then we were making our way down through the uncertainties to talk about error and uncertainty to make sure we were all kind of on the same page. Um, and this was a fairly big deal where, so this is nice. This is where you had the formulas for percent error and percent difference. They might not be explicitly listed in a lab, and so they're there. That's a reference for us. These three major sources of error, well, the categories of how to think about the error, I find those pretty useful. So hopefully you will as well when we try to come up with, major sources of error. We mentioned the inappropriate ones, and we got down to our rules for reporting uncertainties. And so the rules go in order. So the first thing you're going to do is you're going to take your uncertainty and you're going to round it to one significant digit. And then wherever that digit is at, you will then round the value to the same place. Okay. So uncertainty goes first, value goes second, and then they should be reported with the same power of 10 and the same units. Okay. And so that kind of should have allowed you to work on this first part, because they give you that the standard deviation, these are going to be your uncertainties, are these standard deviations, and the means are going to be the, the values, the answers. And so you're going to do one digit here, match places there, and report. And so that's all you have to do for the first part. Now, the second part, what we're going to find is we're given repeated measurements. Okay. And so what we're going to do is we're going to go in and we're going to talk about how we handle repeated measurements. Okay. And what we're going to do is just some simple statistics. Yeah, we'll do the example when we do the second one. So hopefully that'll try to clear some things up. Now, really, to be honest, in this first one, I picked some that make you go, because inevitably that's what you end up with, is the wonky little thing. You're like, now what do I do with this? So to be honest, I picked some unusual ones in that first part. So if you get too stuck, you just need to come see me and we will talk about it. Okay. So let me give you a basic instructions, and we'll do that when we do the example for number 2. Okay. So in this case, what we have are 10 repeated values. Okay, so 10 repeated measurements of the same thing. And so that's an important piece, because you might have like a whole bunch of data, but if they're meant to be different, then we wouldn't run stats on that. Okay, we only run statistics when we have, repeated data that really was meant to be the same. Okay, so we'll make repeated measurements. Of the same quantity. Then we will report our results using statistics. Okay. And so let me make up some fake data. Excellent. I like that idea. And then y'all can talk about it. And again, if you get too stuck, you can come to me and I will help. But I want you to try first. Let's say we have, a bunch of repeated measurements and they're going to be in centimeters. So this is one of those things when you have a table, if at the top of the table you put the units, then the units are implied to be on every element in the table. Okay. And so what I have here, this little I subscript, this is called a counting index. Okay. And so it kind of stands for like, you know, X1, X2. So it's like the 1, 2, 3, 4, 5 when you label out some measurements. Okay. And so I'm going to, again, just make up some, there we go. So there's my data. Now this isn't really, too unusual. This is 1, 2, 3, 4, 5. Okay. And so then we're gonna, figure out what my result is, but like I said, it's pretty straightforward. And so the first thing that we're going to look at is that, how many values do we have in our data set? And so what we have in this set is we have 5 values. So the number of data points is 5. And our result for this, repeated measurement of the same quantity is going to be that, it should be the average or the mean, the arithmetic mean. So to find our average, we kind of know how to do this. We would add it up and divide by how many. Okay. And so, with this particular one here, we have, 2 and 3 makes 5, 4 and 1 makes 5. So 5 and 5 is 10, plus another 5 is 15. So that gives me a 5, carry 1, 5, 10, 15, 20, 25, plus 1 is 26. Okay. And we're going to divide by how many we have, which is 5. And what this will give us is this will give us the average or the mean. Now, I like to use the bar across the top of the symbol to indicate it's the average or it's the mean. And I get to do that because I don't like doing arrows on top of my vectors. You do arrows on top of your vectors, then you have to do subscripts to indicate it's an average or something like that with like an AV or an AVG or something along those lines. But this is my preference. And so when we go and we take 26.5 divided by 5, then amazingly, it's going to go in 5 times, give us 15, go in 3. So this is, 5.3. So that's the average of, 1, 2, 3, 4, 5. The average is 3, But we can pretend like it keeps going, okay? And again, this will be in centimeters, okay? Because you're not guaranteed it would truncate and be real pretty like this, okay? And so this is our value, okay? This is the answer to what did you get for the measurement. We made a bunch of repeated measurements. Our answer will be the average for the mean, okay? But then the next thing is that, well, now we got to figure out what the uncertainty is going to be, all right? And so then what we're going to calculate are what they refer to as the deviations. So we're going to take each individual measurement, we're going to take each one of these xi's, and we're going to subtract off the average. And again, this will be in centimeters. And so these are referred to as the deviations. Okay. Yeah, this is plural. Oh. And so we'll take, 5.2 minus 5.3. I'll write this first one down, but I'm not going to write them all down. So what we get is this is negative 0.1. 5.3 minus 5.3, this will be 0. 5.4 minus 5.3, this is going to be plus 0.1. 5.1 minus 5.3, then this is going to be minus 0.2. 5.5 minus 5.3, this will be plus 0.2. Okay, now what you might think is that, well, we found out how far our values are from the average, that maybe we would average that, and that would be like an uncertainty kind of deal. And the answer is, well, we can't. Because you can see here that you have the minus 0.1 and a plus 0.1, you have a minus 0.2 and a plus 0.2. And so what you get is that if you go in to add these up, you get a whole bunch of nothing. Essentially, by definition of the average, you identically get 0. And if it's not 0, then there's like an issue with round off error or something funny like that, okay? And so then the question is, well, what do we do? in order to get the uncertainty. You can like use how far the values are from the average to indicate kind of a range or something. No, it actually will not be. Okay, but we're getting there. So what happens depends upon what we think the data should look like. Okay, so then what we have is that if we believe that our data should be normally distributed. So if it's a normal distribution of data points, then what that means is that if we were to plot it out, what we're going to plot here are the number of measurements versus the value of the measurement. Okay. Then if the data is normally distributed, then what it looks like is it looks like that kind of bell curve kind of idea, like so. Okay. And then what we find is that this point here should be our average, the mean, and we should have the most data points at that point. And then as you move further away from the average, you get fewer and fewer data points. So this is a normal distribution of data. Okay. And so we believe that this is how the data should look. And a lot of times in order to see this type of distribution in your data, you need hundreds, if not thousands of data points in order to start to see this pattern emerge. But if we believe that this is how it should be, then for most random error, this is kind of how we expect it will look, is something like this. Then what we do is there is a standard procedure for how to get the uncertainty. And so then what they do is they go in and they take these deviations, and what we're going to do is we're going to square them. Okay. So you take each measurement minus the average squared. So this will be in centimeters squared. And so then what we'll get here is that this is negative 0.1 squared. So this will be positive 0.01. 0 squared gives us 0. Positive 0.1 squared gives us 0.01. Negative 0.02 gives us positive 0.04. Positive 0.2 gives us positive 0.04. There we go. Guess I was only going to do the positives on the ones that were negative to begin with, but that's all right. Fix that 0. All right. And now when we go to average them, they won't all sum to 0. They won't all cancel out. Okay, so that fixes that. And again, this isn't too terrible. You get a 1 and a 4 is a 5, 1 and a 4 is a 5. So 5 and a 5 is a 10. So this will be our, 0.10. And then what we find is that there's another little glitch. Okay, now, and this is due to a statistics thing, is that if these data points were the entire population of data that you could collect, we would divide by how many. But what we talk about is that really we could always make more measurements. And so really what we have is a sample of the data that we could have collected. Okay. And if the sample is random, and we're not going to worry about whether it is or is not random, then what you find is that instead of dividing by how many, we divide by one less. And this is because a random sample will always underestimate the variation in the entire population. And so then if it is normally distributed, then the way to overcome that is to divide by one less. Okay. And this is because it's a sample. Now, if that doesn't satisfy you, then the mathematicians have this really lovely class for you to take. It's called statistics. So because it's a sample, then we do one less. If it was the entire population, we would do how many? Now what this will give us is a quantity that they refer to as the variance. Okay. Now this symbol is a lowercase Greek letter called sigma. Okay. And this quantity with the square, this is the variance. Now, if you've had stats, probably having a stroke by right about now, because in statistics, they use the pretty symbols for the population statistics and the unpretty ones for the sample. But the thing is, we only ever have a sample. We never have a population. So then we use the pretty symbols for the sample instead of the pop. So there we go. So 10 divided by 4 goes in what? 2.5 times. So 0.025. And this is going to be in our, centimeters squared. Yeah. All right. So that's our variance. And then in order to get the uncertainty, then what we're going to do is we're going to calculate our standard deviation. And so let me do that.
Professor, can I ask a quick question?
You sure may.
Sorry. So that sigma is n minus 1, or the total number minus 1, and then the variance that you divide by is sigma squared.
Yeah. Yeah.
Okay.
And then we're going to take the square root and we'll get sigma, which is the standard deviation.
Oh, okay.
So we're going to square root it in a moment because we cheated. To do the average, quote unquote, we squared it first. Now we need to square root it to undo the cheat, kind of idea. So now we're going to head to the standard deviation. And so our standard deviation is sigma, which is that square root of the variance, the sigma squared. So that's the square root of 0.025. And this one, I'm not going to know. So I'm going to need help on this one. So what's our value? Is 0.158. Okay. Now the standard deviation, this is going to be our uncertainty. Okay. And this is a choice. We could argue that maybe the standard error in the mean is a better uncertainty value than the standard deviation, but I think for our case, the standard deviation is far enough. We're good enough. And so now we're ready to apply our rules. So we have our value for the measurement, the repeated measurements, and we have our uncertainty for the repeated measurements. And so then what we're going to do is we're going to apply the rules, and we're going to apply them. They go in order. If I can find my sheet, there we go. Found it. So the rules for our uncertainty are that the uncertainty should only have one significant digit. So we're going to take this value, the standard deviation, which is going to act as our uncertainty, and we're going to round it to one significant digit. So then my rounding digit, the check digit is a 5 and the rounding digit is a 1. And so no matter how you slice it, we're going to go to 2. Okay. And again, I don't care how you do that. So then my uncertainty is 0.2 centimeters. Okay. Now this is to apply the second rule. Then the value should be rounded to the same place as the digit in the uncertainty. So my uncertainty, my one digit in the uncertainty is in the first decimal place, the 10th place. Then I'm going to round my value to that same place. And we're going to pretend like I had other digits. I didn't, but that's all right. And so then my check digit is a 0. The rounding digit is a 3. So then when we go in to write our final answer, it's going to be our value, which is 5.3 plus or minus our uncertainty, 0.2 centimeters. So there is one digit in the uncertainty, match the same place with the value, and then they are at the same power of 10, same units. And so this is the process. You're going to take this uncertainty, find the first significant digit, and then round it. Whatever place that is, you'll round the value to the same place. Those are the rules. Okay. Questions?
One more quick clarification, Professor. So just to get sigma squared, it's just the sum of the individual deviations squared divided by n minus 1.
That is correct.
That's sigma squared, and then sigma is the standard deviation itself.
Yes, and that's the square root of the variance, the sigma squared.
Right. Okay, thank you.
All righty. And so now where we are at is this should allow you to do the second one. And the intention is, in general, I just would have you do it by hand. It's 10 data points. It's not too big. We're probably not really going to do this hardly at all, so that's just the deal. So I would just have you, repeat what we did with the 5 data points, but now with your 10. That's right. But then you have to worry, Saeed, that 20 is that indeterminate form, right? Because it's the 2 is significant, but the 0 is not. So you could write it as 2 times 10 to the 1. No, but not 2.0, because that has 2 digits, 2 significant digits in it. It's 2 times 10 to the 1. 2.0 10 to the 1 has got 2 significant digits. Okay? And so this is where like powers of 10 could come into play. And if you have to do powers of 10, then the way we should handle that is your value, the number itself that we're reporting, the mean. This should be in the power of 10. You should move that into scientific notation. And then whatever number of places you move the decimal for the value, for the mean, you would then move it for the uncertainty to be the same. So if we go in and let me pretend this looked different. So let me do an example. So let's say that this was, 5,300. And so then this would be plus or minus, 200, I don't know, units, whatever. Okay. And so we got one significant digit. Here's the 2. It matches with this place, the 3. So then these zeros just hold place. So what you would do is you would go in and do 1, 2, 3 places to the left. So that will make this 5.3 and then times 10 to the 1, 2, 3. And you do the same 3 here, 1, 2, 3. And so this would be plus or minus 0.2. All of that times 10 to the 3rd, and then whatever units you have. So you put this value in scientific, and whatever number of places you do this one, you do the uncertainty to the same, because I have to have the same power of 10. Okay. I don't think you'll run into that one a lot, but you might. So, okay. All righty. Let's talk about our graphs. So that'll give you at least a way to start the first 2. And again, you might get stuck. You might have questions. You come see me, or, form good study groups and work with your classmates. I encourage that. Make sure we apply the rules, put them in order. And then let's take a look at number 3. We're going to make a complete graph. Okay. And so this is what I mean by a complete graph, is that it needs an appropriate descriptive title. So we need the title, label in units on each axis. The no connect line is, I don't think we need that. It used to be in an earlier version of like the Logger Pro program we used, it would automatically connect the data points. And you don't want that. I mean, we're not in kindergarten connecting the dots in order to draw the doggy in the picture. I mean, it's by connecting the dots with the line, you're implying there's no uncertainty in the data points, and that's just not true. So we don't want that, but it doesn't come up anymore. So they changed the program, so I should probably update my sheet. That's what it all means. We need a best fit line with the uncertainty in the regression statistics. That's the part that's hard to do on other graphing programs, to be honest, is to get that little bit. It's super easy on Logger Pro. Okay. So these are the things we want. And we're going to go in or make this graph of speed versus time. Oh, let me put this down here before I lose my camera. Okay. So one thing I need you guys to either recall or to note. It is always y versus x. There are no exceptions to that. It is always y versus x. So when they give you this description here, speed versus time, it's y versus x. So speed will be on the y-axis, time will be on the x-axis. That's the graph we're asked to make. Okay. And so we'll want to go in and, put this into our data. So let me go in and let's open up the Logger Pro program. And I'm going to, share my screen when I do that. So let me stop sharing here. Come over to here. Okie dokie, let's try that again. Oh, good. Thank you, Brittany. All right, so there's my version of Logger Pro. I saw something quickly ago that it was graphical analysis probably will work just fine. I think it only does the graphing. It might not do the data when we get the data sets, but we'll have to see. I think that'll be all right, to be honest. It'll do the graphs, I know. But the question is if we have the raw data set, if it'll open that up and allow you to manipulate it. And I guess I don't exactly know the answer to that. Okay. All right, so now we're going to make our graph. Now, the basic idea here is that if you double click on something, you get the options. Okay, so it actually is a fairly intuitive, easy to learn program. Unlike Excel. If it was Excel, then by the time spring break comes around, you might be able to make your own graphs. I wouldn't need my help. But with this one, probably by the second or third one, you're good. And so it goes a lot quicker. Now, the number one thing we got to remember to do is you don't want to start on the axes. You want to start on the data table. So I'm going to come over to here and I'm going to double click on this Y. And here are the column options. Okay. Now we said that is always Y versus X and it was speed versus time. So the Y axis should be speed. So we're going to give it the name speed. The short name is in case we don't have enough room on the data table to fit the full name, then it'll default to the short name. I tabbed over, but you can click with the mouse either way. So I'm going to go and put the, the magnitude of the velocity for the speed. So put V. And then the units are going to be in meters per second for SI units. And then notice that these little pull down arrows here, you can get things like degrees. You can get Greek symbols, Greek lowercase, Greek uppercase. You can do subscripts, which aren't terribly useful, but superscripts, which are very useful because you could do something like meters per second squared, which isn't right, but you can do it. It looks pretty. So you can do the little squares. You don't have to do like the caret twos. We don't need that here, but that's okay. Then what we're going to do is we're going to hit done. You can also hit enter or return. Since it's highlighted blue, then it'll do that. And notice what it does for you. It puts the label, the name, and the units on top of the data set on the table. It puts the name and the units on the axis for you. So this is the deal. You want to do it on the data set, not on the graph. If you double click on the graph, it does all sorts of funny things, and usually it's just easier to start over. So then let's do the same thing for the X. Again, double click here. It'll give you the options. And this is going to be time. The short name we'll just use a T. And then it's going to be in seconds. And then we can do either mouse to the done or hit enter. The other thing is you also get options on this. And you can change what things look like or whatever. So yeah. There we go. So now we have labels and units on our axes. We're going to go in. I'm going to have you fill in the data table. So I'm just going to click into the data table and we're going to take our information from the chart that we were given. And then we're going to put it in. Now, one of the things you'll notice is it dropped my ending zeros. And so now they only look like they got one significant digit in there. If we come into here and look at my options, down here, this is in the displayed precision. It's set to be automatic. But we could go in and we could say either decimal places or significant figures. We're going to do decimal places, and I'm going to force it to show 3 decimal places. And then when I do done, it shows them. So we can fix that. I don't think it was bad that they disappeared, because it's a computer. But if you want to show them, we can make it show them. And again, that's double click to get the options. Then you have to do this tab over here, and it's this piece down here under displayed precision. Okay. Not necessary, but can be done. All right. So now what happens is it automatically plots our data points. And you can see them down in here, but they're all squashed into the piece. Sometimes when you put them in, it depends on how you load it, it might actually scale the graph with it, but mine did not. So we can fix that in one of two ways. One option is we can come over to here, this little button above here. This is the auto scale. We click that, it'll make the data fit the space, which is great, except that we kind of lost the origin. And so if you wanted the origin in the graph, then we'll need to fix that. So that was the auto scale button here. Like I said, if we aren't happy with this, the other way to fix what we had before is we can come into here and click on that lowest point and then type it as 0. And we can force it to shift how to do the graph. Okay. I think this looks okay. Maybe we might want to come over to here. And this looks fine, I guess. We could go to 0.06. So then my graph's a little more in the picture, like so. So to change the scale, you just click on the extreme points on the scale and you can retype in the values by hand. You do the auto scale. I mean, it was fine. I mean, you don't see the origin, but I don't know if that's, in certain cases, it's important. I don't know if it's super important for this one. It would have been fine if I left it. Okay. All righty. So now I have my data points, no connect line, label in units on each axis as appropriate. Notice it put in the parentheses for us automatically. Now I'm going to put in the title. Okay. So you're going to go anywhere on the graph that's not a data point and double click to get the options. And this brings up the graph options. You can also get to them from pull down menus up here, but I like the double click. I think it's pretty easy to pick up. The first piece tells us what is the title. And then down in here is where we would unconnect connect points that we don't have to do. So the title that we're going to do, you need to give it a good descriptive title. So the title should essentially tell the reader what they're looking at or what they're going to get from that graph. Okay. So, you know, we probably shouldn't just label it as Y versus X because that's kind of like statements of the obvious. I mean, you can see the axes if you can see the title. So why did you tell me the axes again? The title should differentiate. This is this set of data versus that set of data, or this is this graph and you get this from it versus that graph and you get that from it, kind of things. So we'll want to try to come up with a good title. Should be better than this one. This one won't get you full credit on the lab if you put it in. So let me warn you, but yes. All right. So I've got, hopefully you got a way to put in a nice title, something that tells the reader what they're looking at on the graph or what they're going to get with the graph or why this graph is different than the other three that are nearly the same in the lab. You know, something along those lines. That's what you want to strive for with a good title. Then what we need is our best fit line. Okay. And so we get options up here. And this one here, this is the linear fit button. So we don't want to necessarily do the curve fit button. We want to do the next one over, the linear fit button. And if we click that, then it should do the best fit line. Now, one thing you got to be careful with is if you have things highlighted like this, selected, then it'll only fit the selected region when you hit the button. So this fit is not the same as that one because I highlighted, you know, not all the data points. So you either need nothing selected or all of it selected when you do the best fit. Okay, let me close that one out. You can tell where it is by these little brackets. You can technically grab a bracket and move it. So now I left out that data point, which we don't really want to do. But I can put it back in again. Go. No, just things that can be done. And so then here we have our slope. Here we have the intercept. You can see it's very, very close to the origin. That's nice, I guess. And then what we can do is we need the uncertainty in the slope and the intercept. These are called the regression statistics. And so then what we're going to do is I'm going to double click on the box and we get the fit option. Pretty much you double click on things, you get the options kind of idea. Again, start on the data table, not on the graph itself. And we go from there. This allows us to alter, what you see is the result. At the moment, we're getting 4 significant figures in our results for both the slope and the intercept, which is fine. But what we want to do is we want to do this show uncertainty. Okay, so if we click that and then do OK, it'll put them in. Okay.
Really quick, could you say again where you clicked to get the box for the linear fit options open? Did you click a data point?
No, actually, we clicked the linear fit box itself.
Gotcha. Okay, thank you.
Mm-hmm. Anything else? All right. Then we will need to submit the graph. And so that's going to be done one of 2 ways. You're going to either print it if you have a printer, and then you could scan it with your rest of your stuff. With the Genius Scan or whatever phone scanner you have, that's fine. If you don't have a printer, that's okay. Then what you're going to do is you're going to take a screenshot and then try to save it as a JPEG. Then you can go to the Sejta site and you can convert the JPEG to a PDF. You can then merge that PDF with the PDF of your other stuff to get one single PDF file. You will need to report your slope and your intercept according to the rules. And so you'll take the uncertainty and round it to the first significant digit. And wherever that is at, you'll round the next one to the same place. Okay? You'll round the value to the same place. Questions?
Are you saying we need to do that for the uncertainty as it shows up in this box right here
That is
on the
good.
graph?
Yeah, but we won't be able to fix it on the graph itself, though.
Okay.
Because if you fix one, you'll mess up the other. So just leave it like it is here in the graph. And then, you'll report either on the graph itself or on your other sheet. You'll say the answers are, this is what I got for the slope, this is what I got for the intercept, and, apply the rules. 1 digit in the uncertainty, match places with the value. Don't forget your units.
Okay, thank you.
Mm-hmm. Yeah, but you can't fix it on the graph, though. I mean, if you get super lucky, maybe you could do it, but it's not worth even trying. It's not expected. So
Would a title of like lab 1 and then a description of what this graph is showing, like a word, would be sufficient?
I think that would be okay, especially if you happen to mention what we got out of. See, the thing with our graphs is that we usually graph things so that the slope is what we want. And so very commonly, you might tell me what the slope gives you.
Great. Thank you.
Mm-hmm. What else? Well, I guess I didn't do my timing very well because we're kind of done. I hate that we have 10 minutes I didn't use, but I don't think I have anything else I can really start, So what you'll want to do for next Tuesday is you'll want to go in and read more in 17. We're going to start in. We want to remind yourselves about how to do vectors and components and things like that, because we're going to do the electric field, the electric force, and then the electric field. So we're going to talk about Coulomb's law, which is the electric force between point charges. And it's forces are vectors, so it's a vector quantity. And then when we add vectors, you'll want to do them, by components if it's in 2 dimensions. So you'll want to kind of remind yourself of those things for that particular class. We pretty much finished up the first lab on uncertainty and graphing. The next lab we're going to do is going to be that one that we were watching the video for earlier with the charges and the electroscope. But yeah. Questions? Do I need to show anything else? Everybody do okay?
Hi, I have a question. Can you hear me?
Yes, I can. Go ahead, Anna Luisa.
So I think I missed a little bit. My computer is kind of freezing of when you were explaining question 1.
Mm-hmm.
So basically, I'm a little confused. I don't know. I was wondering if you could walk through it again, or like I was still like a little bit confused on the standard deviation, because does it only have one sig fig, or is it only to one decimal place? Like that's what I was a little
Right.
concerned about, like confused about.
Now, my example I did in class, let me reset things up so I can show. And let me check on Brittany's question here real quick while I'm on this computer. Yes. So, Brittany asked if the due date is correct, and it is, because today is the 18th, and we completed the lab today, in my opinion, so it'll be due 1 week from today, so it'll be due on the 25th. So next Thursday at 11:59 p.m. it'll be due. Okay, so that seems correct. And then let me share with my other computer so I get my, so I can write, and then I can answer Anna Luisa's question. All right, go. So let's go and let's say that we have a different uncertainty. Go. That's right, Megan. You're just gonna, I tried to put in the Blackboard piece what you need to submit. You just need to submit your answers to part 1, your answer and your work to part 2, your answer and your graph to part 3. And they need to be just one PDF document. Yeah, so there's no written report on this one. There's only going to be a couple of those anyways. Okay.
Okay, so if we wanted to just include that on the PDF of this lab sheet itself, we could do that, or just we could write our answers on a blank sheet of paper.
Yep.
Okay, thank you.
That's correct. All right, so let's go over Anna Luisa. Is that right? I think that's right. So let's say that we have a mean and a standard deviation that are, something else. Say this is, I don't know, 0.05432, and this is 152.1145. These are going to be in, I'll put meters or something. I don't know. Okay, so what you basically do is you look at the standard deviation first, because it's our uncertainty. And the first rule is the uncertainty should only have one significant digit. And so when we look at this value, you need to remember that leading zeros are not significant. So the first significant digit is the 5. And then we're going to round based off of the next digit, which in this case is a 4. So then the 5 just stays no matter how you round. Now, you can run into funniness, like if the digit causes you to round up. So then, if this was like a 9 and this makes you round up to 10, then do we have a 9, or, where do we at? And so that's an interesting point, and so you just need to make a choice. You could say, well, no, I was really in this second decimal place, and so it should be 10 just because it rounded. Or you could say, no, it's one in the first decimal place, and that's where we round to. As long as you're consistent with whatever choice you make there, it'll be fine. So this is our plus or minus 0.05 meters. And then since this is in the second decimal place, then we go to 2 decimal places here and round. Now, again, the 4 is our check digit, and so the ones will stay. And so this will be, 152.11 plus or minus 0.05. So there is one significant digit in the uncertainty. It matches with the last digit reported in the value. And so those are the 2 rules. Okay. Now, things can be different if they're larger. Like someone asked, I think Saeed asked earlier. So if my standard deviation is 391.4, and we'll say this is 15,143.2. So, okay. Then again, we apply the same rules. You go first significant digit. Well, this one's fairly straightforward. Is that 3 is our first digit, and we'll round based off the next digit. And so then what we get is we get that this would be, 400. But again, the problem with that is that's indeterminate. Now we know the 4 is significant, but these zeros are not. Those are just holding place. Because if you just write 4, then that's a different number, right? It's a 4 in the hundreds place. And so then when we match places, we need to go to the hundreds place and then round. Okay. And so then this would give us 15,100, where again, we know these zeros are not significant. But in order to write this, then what we would do is we would put the value into scientific notation. So then we would get, moving it 4 places, this is times 10 to the 4, right? Then we would write that this is 1.51 because these zeros didn't count. This 1 in the hundreds place did, but the things behind it did not. And then what you do is you do the same thing. 1, 2, 3, 4. And so then what we get is this would be 0.04 times 10 to the 4. And so I would probably put it together and we would get 1.51 plus or minus 0.04. All of this times 10 to the 4, and I wrote centimeters squared. One digit, match places, same power of 10, same units. Questions? You're welcome. Anna Luisa, is that right? I can't see my people.
Hi, can you hear me?
Yeah.
Yeah, thank you. That definitely helped a lot. I have a follow-up question if that's okay.
Sure.
I was wondering if the standard deviation could be larger than the mean,
Yeah.
because I saw that there was a yes.
Mhm.
Okay. And
I
in
mean,
that
so the question
case,
is, you need to consider, well, what if the value you were trying to measure, what if it should have been 0? Like the intercept on our graph. What if it should have been 0? Theoretically. Well, then you might expect to get an answer of zeros so far out, and you can go and say, well, I agree with 0 up to this place, and then we're uncertain by this many units in that last place. And what if the value we were trying to determine or trying to measure should have been 0? Then what would we expect to get? Well, you'd expect to get an answer of 0. We'll 0 out to so many places before we reach our limit of precision in the experiment. So
Hmm.